Let's continue lesson 4.5. Now, I'd like to make a little comparison with where we've been and where we're going to go. You see, in our last lesson, we talked about something known as a linearization. A linearization is an estimation of a y value. Today, though, we're going to talk about a differential. And you see, a differential is an estimation of a change in a y value. So similar, but different. And let's dig a little deeper now into this idea of differentials. And to do that, I'd like to start with a familiar symbol, a familiar calculus symbol, that is dy dx. Now, dy dx, we should know, stands for the derivative. And we can also say that that's the same as f prime of x. But have you thought, I'd like you to think, about how dy and dx actually represent something. You see, dy represents the change in a y value, or to say that the change in y. And dx, well, that represents the change in an x value. Now, where have you heard that before? Where have you heard change in y over change in x? Yeah, that's right. It's the slope. Of course, we know that a derivative is a slope. But if you kind of think about the numerator and denominator separately, we could separately say that dy is the change in y. And we could separately say that dx is the change in x. Now, if I take this equation and solve it, if I take this equation and solve it for dy, it would just be a matter of multiplying this dx over to the other side. But when I write it in this form, that is that dy is equal to f prime of x times dx, I end up with a special concept. It's known as a differential. And you see, a differential is when we have separately the symbol dy, that is the change in y, and now we can say that it's equal to f prime times dx. What does this mean? Well, if I ask you to find dy, that is the differential, then I could use this formula where I take the derivative of a function, how about of x to the fifth plus 37x. Now, when I take that derivative, I kind of take it, well, as a differential, meaning that I just determine dy, which is going to equal f prime. Now, f prime of x to the fifth is, well, 5x to the fourth plus 37. Nothing real tricky there. But it has to get multiplied by dx. And basically, when I'd write it in this form, I end up with a formula for the change in y, for the differential. A differential is when I separate the dy and the dx. And specifically, when I separate it such that dy is equal to f prime of x, that's the derivative, times dx. Now, remember, what does dy stand for? That's right, it stands for the change in y. And to be a little more specific, it's the estimated change. What does dx stand for? Well, it stands for the change in x. So again, when I separate these two variables, I end up with what's known as a differential. What do we do with this? Well, quite simply, we use this formula to find, that's right, the estimated change in y. And then we often will compare it with the actual change in y. Sounds like a lot of mishmash. Well, let's work it out with an example. Okay, what we're going to do is we're going to find dy at a equals 1 if dx equals 0.02. Now, the good news here is that all this really ends up being is a derivative. It just ends up being a derivative in a differential form. And a differential form is when I split dy and dx. So let's try it. Now, I'll do the derivative. That is, we'll find dy. And we do have to notice that to find that derivative, we're going to end up using a product rule. So I got to work through that product rule no matter what. So that's going to be the first times the derivative of the square root. Now the derivative of a square root, remember, is the same as an exponent of 1/2. So what you're seeing me do here is bring down the 1/2. But of course I have to finish the outside derivative, that is doing changing the exponent to be -1. And then you got to do the derivative of the inside. That's called the chain rule, but the derivative of the inside is just 1. That's just the derivative of first, or that's just the first times the derivative of the second, plus the second. Now the second is going to still be this square root function, 1 plus x, times the derivative of the first. And that'll be a nice little 6x squared. Okay, now that's the derivative, but according to the definition, it has to all get multiplied by dx, because basically I just multiplied or just moved that dx over to the other side. What is this? Well, it's something that needs simplified, but again, it's a differential because basically I've split up the dy and the dx. But I also wanted to use this example as an opportunity to talk about simplifying something like this. So what do we see here? Well, I hope we see some things that can cross out, like the 2 and the 1/2. We also have a negative exponent, and we've been in this place before, so we have to be willing to turn that into a denominator. So I end up with x cubed over 1 plus x to the positive exponent of 1/2. Now over here on the other side, we don't really have anything that can be simplified, but maybe we can kind of get it prepared. That is, we can get it prepared to interact with the fraction that we made. So I'm going to change the square root to also be a 1/2 power. But of course, there's nothing negative about that. So it's just 1 plus x to the positive 1/2. Okay, are you ready? Are you ready to make a common denominator? We have to be willing to do this. We have to be willing to put a 1 plus x to the 1/2. We have to put that in the denominator, but that means we also have to put another one up in the numerator. So I put a 1 plus x to the 1/2 in the numerator. Now that conveniently is going to interact nicely with what was already in the numerator. That is, it's going to allow me to add these exponents. Now if I add those exponents of 1/2, I end up with just an exponent of 1. So I end up with 1 plus x to the first power. How about, let's break this down a little bit. Let's make sure that we see these steps. Over here, I end up with 6x squared times 1 plus x to the first power. We don't really need to write that first power. But notice now that I do have a common denominator of 1 plus x to the 1/2. And I'm really just a step away from simplifying this to be one fraction. Okay, that is if you see that we can do a little distributing. And once I do that distributing, I can combine some like terms. Looks like I'm going to have a 6x cubed that I can combine with the existing x cubed to give me 7x cubes. I'm also going to end up with a 6x squared. Nothing becomes of that, but I do end up with now a common denominator. Now, I have to admit that I've been a little sloppy with the dx that we wrote down. It's still here. It's still been, if you will, multiplied to the other side of the equation. But it's important. It's important because now I have a formula. I have a formula for dy. And that formula for dy is basically the derivative, this crazy fraction that we found, times dx. And dx is going to end up being part of my given. If you go back to the given, I hope you can see here that we have an a value, that is a x value of 1, and then we have a dx, that is a change in x of 0.02. It's actually quite simple. All I need to do is just plug these numbers into my formula, because that's what this is. This is a formula for dy. So I'll plug in 1. That was kind of purposely given because plugging in 1 is, again, pretty easy to do. I'll continue to plug in 1, again, into my formula. Now, I will also plug in 0.02. I'll plug that in for dx, and that's something that's going to get multiplied by my derivative, by the value that I get for the derivative. Okay, that's something that I hope that you would think about. It's basically 7 plus 6. That comes out to be 13. If you look at the denominator, we basically get 1 plus 1, which is 2. But that is to the 1/2 power. So we can kind of like reinterpret that as the square root of 2. And that's still going to get multiplied by 0.2. And when you multiply that all out, you get 0.184. Now, what is 0.184? Well, simply put, it's the estimated change in y. Okay, so we found dy. I'm going to add something to this problem. I'm going to ask us to now compare the actual change with this estimated change. And don't forget that this estimated change was that 0.184 number that we found, but we want to compare that with the actual change. Now that means that we need to find the actual change, and to find the actual change, we need some actual y values. And I'll say kind of candidly that this is not really a calculus question, because when we're talking about actual values, we're just talking about plugging in x so we can get y. Okay, so we have to do a little bit of plugging in. Now, you got to kind of keep track of what we're plugging in. And first thing we need to do is plug in that actual first x value. So we plug in x. Keep in mind that what's happening here is that we are seeking a actual y value. All right, but that's easy to find. If I could just plug in 1, I'll end up with, it looks like 2 times 1 to the 3rd power times the square root of 1 plus 1. I think that's going to come out to be 2 root 2. If you'd like, you can turn that into a decimal. We actually will work with decimals often in this lesson, so it's fine to change that to 2.828. If I'm going to find the change in y, then I need another y value. And here comes the part of basically the problem where you have to realize that the other y value comes from the other x value. What other x value? Not 0.2. That's right, 1.02. You see, I got to take these two numbers and I have to think about doing what they say. I need to change by 0.2. And if I change by 0.2, that means I'm now at 1.02. Okay, so my first x value is 1. My second x value is 1.02. Okay, so we plug in 1.02. I'm going to skip showing that, but you could plug it in and you end up with 3.017. Make sure that you understand that came from plugging in to the original function. We're just about there. Do you realize what we have to do? You realize what we have to do with these two y values? That's right, we have to subtract them. Now, when you subtract them, you always subtract second minus first. So it's 3 minus 2. With all the decimals, we're going to end up with an actual change in y. An actual change in y, when I subtract these numbers, of 0.189. Now, we're supposed to compare, and that means that we need to take the original estimated change. We have to take that original estimated change, which, what was it again? It was 0.184, and subtract them. If you subtract them, you're basically comparing them. And I'll tell you that it really doesn't matter if it comes out positive or negative, because what we typically call this is the error. And the error, being the comparison between these two numbers, is just the absolute difference. So if you subtract these numbers, you get 0.005. And I'll tell you that that's supposed to come out to be a small value. It did, but of course that's just kind of relatively speaking. What's going on here? do all these numbers represent? I mean, even right here in this screen, we have X values, we have Y values, we have change in Y values. And then on top of that, we have an estimated change. Well, I prepared this pretty descriptive graphic, which is supposed to represent everything that we've done in this problem. Make sure you take some time and let this sink in, draw a sketch, pause the video if you have to. First of all, the red line that is drawn, well, that's f of x. That's actually the original function. You know, the 2x cubed times the square root of 1 plus x. Now we also have some x values. We have an x value of 1, and we have an x value of 102. If I can get that looking a little better. And then I hope you notice that we have a purple tangent line, and we also have some points that we want to apply to this problem. And what I want you to apply is how each of these numbers fit onto this graphic. Now, if we were in class, I would challenge you to fill these numbers in. So I'm going to challenge you to do the same thing right now. Would you be able to fill in any of these values on this graphic? I hope that the first one, dx, is one that you feel like you can fill in. That's the change in x. Are you getting the idea that the change in x is how we went from x equals 1 to x equals 1.02? So I feel like we could pretty confidently say that this space right here, this distance, would be the 0.02. Again, it's the change in x. How about the estimated change in y? How about 0.184? Now, that's the change in y, but it's an estimated change because it came from the derivative, or more technically, the differential. Well, that means, yes, that means it's going to be a change on the tangent line, because a tangent line is always the line that is connected with the derivative. Now, what I'm trying to show you is the space between those two y values, the distance between those two y values. That is going to be dy. That's going to be the 0.184. Okay. Finally, we have the actual change in y. The actual change. Yes, that's right. That's going to be another distance between two y values. But this time it's going to be an actual distance. That means it's going to be on the actual function. That is that red function. So the space between those two green y values, yes, that is going to be 0.189. Now, it is not drawn to scale perfectly, but what we're supposed to see is that these two changes are similar. They're so similar that they only differ by the error that we found, that 005. Okay, so our yellow change is an estimated change. It's a little small. Our green change is the actual change. Okay, but the point here is that these both represent changes. Because remember, today's lesson is all about the change in y values. Sometimes students will correctly ask, why do I need to estimate change? Well, honestly, because it's a theoretical concept. And I want you to understand that a differential is how we end up calculating an estimated change. So let's try it again. And I'm really going to encourage you to try this one. This is a time to pause the video because I'm going to ask you to find dy. That's an estimated change. Okay, now remember that comes from our differential formula, where you're going to find the derivative and multiply it by dx, because you're just going to separate dy and dx. Okay, so see if you can do that for this specific problem. And then if things are really rolling along, you can compare the actual change with this estimated change and see if you can come up with that absolute error. All right, so we want to find the differential. It's just the derivative. The derivative of x squared is 2x. The derivative of x is 1. Now, it's just the derivative with the dy dx separated. So we have to, technically, we got to get this dx symbol now written on the other side. That's a formula. It estimates change. Okay, it estimates change when I plug in an actual x value, when I plug in 2 for this problem, that is. It also estimates change when I plug in the change in x. So we plug in 0.3 for dx. This problem is supposed to be a little bit easier. It doesn't have quite a complicated derivative. In fact, it just ends up being 5 times 0.3, which is really 15 with the decimal moves one place, otherwise known as 1.5. Okay, so 1.5 is our estimated change. What do we need to do next? That's right, we have to find the absolute change. Okay, now the absolute change comes from some absolute y values. My fault, I really shouldn't be saying absolute. I'd rather say the word actual. So the actual change comes from some actual y values. Okay, where do we get actual y values from? By plugging in x values. Okay, so we're going to plug in x equals 2. Now be careful, you want to plug this into the original equation. The original equation was quite simple. It just was x squared plus x. Obviously for this problem, then 2 squared plus 2. All right, so we get an actual y value of 6. We would need another actual y value. Now, it's important that you realize that this comes from thinking about the original x value of 2, but my change in x of 0.3. Yes, that's correct. That means I'll be at an x value of 2.3. All right, so you plug in 2.3, square it, add it, and we end up with 759. Okay, now we haven't found the change until we subtract these numbers. When you subtract these numbers, pretty simple subtraction, and again, we'll call that the actual change to be 159. Now, if you're doing this right, you're supposed to notice that, well, the two values are similar. Okay, one of them is an estimate, and one of them is the actual. But if you take your two numbers and subtract them, I'm talking about my estimated change with my actual change. Now remember, the estimated change was dy. My actual change I just found. And it really doesn't matter which way you subtract them, because we really just want the absolute error. So yes, this is going to come out negative, but when I do the absolute value, we'll just go ahead and switch it back to 0.9. So basically, the two changes only differ by 0.09. Okay, and that's our comparison. How can we use differentials in an application? Well, again, it's more of a theory idea, but I like this application problem. It should tie some ideas together for you guys. Take a look. We're going to estimate the change in volume of a cube, and we say that the edge of the cube is going to increase from 3.5 to 3.8 centimeters. All right. Now, just to be clear, if you really wanted to, you could find the actual change in volume. I have no doubt you could find that right now. But what I really want you to do is I want you to use differentials so you understand the calculus idea to get the estimated change. So are you kind of picking up on what's required to get this differential? Yeah, it's required that we have some x values. And I want you to interpret these two values as your x values. But in particular, I want you to interpret the first x value as a. Now that's pretty important, okay, because a is always where my graph starts, or in this case, where my cube starts. So we're going to think of 3.5 as A. What are we going to do with 3.8? Okay, well, we're not going to say that 3.8 is our other x value, but we're going to use 3.8 to help us get the change in the x value. Okay, so notice here that I have my starting value and then I just have my change. Okay, isn't that all you need to do a differential? Well, let's make sure that you understand. So we'll start with the volume equation. Now, volume of a cube is just x cubed. We've had some more complicated volumes, but in this case, it's a cube, so it's just x cubed. Now, my differential, we'll call dv. I want you to see that notation. We can use dv instead of dy. It's just going to be the derivative, which is 3x squared. But remember, you have to get that dx. You have to have that dx on the other side. You kind of like separate it over. Take a look. The whole idea here is that this formula is awfully simple because it only requires you to have a starting value. Well, I think we figured out that the starting value is, remember, 3.5, and it requires me to have a change in my x value. And we decided that the change in x value is 0.3. The whole idea with the differential is that it's supposed to be easy to find because you just plug into the formula. Okay, you don't have to find other numbers. You just need the starting number and the change in the numbers, the change in x. All right, and you would pop that into a calculator. That's expected, and you end up with an estimated change in volume of 11,025. And I guess we could say that that would be like a change of 11 centimeters cubed. Now, even though I didn't ask you to do this, it's not bad for us to think about the actual change. And the actual change, as we've said a couple times, comes from actual values. Okay, so yes, I'm going to need the actual volume at 3.5. And as we already said, that's pretty easy to find. So I can just plug in 3.5. I can cube it. We end up with 42,875. But I would also need the actual volume at 3.8, right? Yes, so the actual volume at 3.8, plug that in, and we end up with 54. So what do I have to do with these numbers? Right, we have to subtract them. Now, when you subtract them, you get the actual change, which comes out to be 1199, but I believe it was supposed to be exactly 12 just because of the rounding. So how do we do? Well, it's not like we made any mistakes, but we just want to compare and realize that the estimated change compared to the actual change, yeah, they're different. But that's okay. Okay, they're different because they're both describing a different thing. One of them is a change on the tangent line, that is the differential, and one of them is the actual change on the actual function itself. All right, well, now it's your turn, of course, to take a look at assignment 4.5.